但是12楼看看没人来就走了，学生也没来就走了。我在2楼便宜，2楼没人来，溜了。There is some cost.
12, 15. 15.
Thank you.
Because there's a lecture right before this one and they don't want to have problems of it spilling over or finishing late or stuff like that, then every when they moved us to here, then by definition they moved us also 15 minutes late.
Yeah.
Wait, lectures here today?
קבוע.
קבוע?
קבוע. מצא מוצק פה ב-12 ורבע. יום ראשון 221, יום שני פה. קבוע.
ברבע.
כן. אלא אם כן הוא שולח לכם מייל, אני אם כן מצא ספציפית בשביל מסוים. אבל כן, היה מעניין להיכנס לפה כדי לנקות אחר כך ולזהות את הפנים של המרצה האורחת. שקמה ברסלר. זה כזה,
היא עובדת בסרט.
במכון ויצמן.
לא, היא קשורה גם למקום של המאץ חידושים בשוויץ.
בסדר.
בסדר, כן.
זה כבר שאלה של מה התחום שלה.
זה התחום שלה.
יש הרבה דברים שעושים בסרט. אז להגיד זה התחום שלה זה הרבה רחב.
היא קשורה לשם.
איכשהו, כן. מקווה שלא חיכית יותר מדי. הופלה. מה מצב הווליום פה? 24. I wonder I didn't hear a thing.
מספר האנשים בקורס הזה...
הנה שרוק ואחותו.
פרק הגיל שאנחנו כל פעם יותר ויותר קצת.
שמים אותה.
לא, זה בתרגול בהם יותר אנשים.
נכון, כי אנשים לא מבינים לעולם, זה פשוט. שמים את האוכלוסייה המקומית. כל מי שנשאר ממש...
לא, אבל אז איך רואים, כאילו ביוטיוב רואים מקום?
באים פה מעמיד, כאילו, ראש בין מעמיד השלום.
אף אחד לא מעמיד, אנה.
לא, אני כזה גם רואה פלטות במהירות של 1.5.
הנה, אנה נכנסה איתה, היא הייתה היחידה.
פעם היא
היחידה וגם פה כל הייתה היחידה.
וואלה, לא ראיתי שהיא נכנסה, אבל בסדר.
לא, וגם אם משמיעים את זה ביוטיוב. זה... זאת
לא
ההקלטה?
שומעים כלום.
זאת ההקלטה?
כן.
למה נוסע עכשיו אופטיקה? למה נוסע עכשיו אופטיקה?
אני לא עשיתי בזמנו. גם התיכוניסטים עושים עכשיו. עושים ביחד.
בוא תתחיל את זה עכשיו, לא זה משנה.
אני אבדוק בטלפון שלי אם שומעים.
אני יודע שהמחשב הזה משום מה לא זה.
כן, שומעים.
מה, האופטיקה הזו?
הרצאה 13 שומעים.
לא, זה ברור שיהיה, אין סיבה שזה יהיה התקלה.
פשוט לא שומעים במחשב פה משהו.
כן.
אני צריכה להשאיר. יפה שיש לנו עוד שבוע ברוכן.
לא יקצור אותו.
ברור שהיא תדחה אותו, כי יש לנו רק שיעורי בית 4.
יש שם מתחיל עכשיו 5.
סבבה, אבל היא לא יכולה לעשות אותו כי הוא להגשה אחרי הבוחן.
אני לא יודע. תעשה מה שאני
היא גם אמרה שהיא תעשה אותו, את הבוחן הזה על שיעורי בית 4 עד 7, והיא לא הספיקה.
כן, זאת הבעיה.
נראה לי תדחה את זה בשבוע, שבועיים לפחות.
כן, פשוט היה אותי שבוע תתעצבן. כל שני חומרים של חומרים שיש בשער ביחד.
היא לא יכולה, אין לה.
אני פעם שעבר נתמחת שבוע ראשון, חומר של שבוע ראשון ביחד.
חשבתי לה, אבל שוב.
כל הכיסויים של ביחד.
אני לא מצליחה להעביר ככה, כי יש ביטות וכאלה להעביר.
מה? מהטאץ' אני לא רואה משהו שאמור להיות בעיה. כאילו אני עושה טסט, וניסיתי להפעיל גם ביוטיוב, אני לא... כאילו פה, כאילו זה המזל נכון, זה גם גבוה מספיק אפילו. הוא אומר את זה נכון, גם... כאילו, יש איזשהו חיבור כלשהו לרמקול.
今天肯定没有，今天不知道有没有。飞机票什么时候买啊？我操！哎，我俩你是准备7月交，你报上交了吗？
哦，那个我没报。飞机票有，
好像是上交最早是7月8号，
机票要不就前3号，选3号。
还好从上海坐到西南看，然后再坐回来。6号飞过去直接参加，反正都在浦东降落，上交了。我操！倒不倒吧？上交前2天让参观前让你听讲座，没什么用啊。后2天才是与专家一对一交流，看看流程表。为啥我们可能是下一个后备一下午困境到了1点，我们下边赶上直接特殊上的
Ah, to już jest dosyć to?
Focul pe dacă șești că deci nu faci
我们都要清理在他之前，不大概有在，大概在这附近，就是3号到6号，3号到6号选个时间。
3号到6号。
但是6号基本上最便宜的，6号飞直飞浦东那个
有点赶。
非常多，1000多。
我还没看呢，我还没看到都。
כן, זה אחרון שספציפית תקוע. זה מוזר.
אבל קצר, לא?
ושאלית על זה.
נעשה טלפון אחר.
ושאלית על זה.
טלפון אחר זה כבר יהיה...
8号飞进不了，
7号还有一天。
他是6号从这儿走，好像是7号 走要飞13个小时，直飞到湖南，然后从这儿一下午飞到那儿的时候，刚好是那边的早上。
那边不是早上了吗？
我不知道，我没看那边，我看一眼。
那边就是下午了，
他们下边我不知道，我看一下。
הצלחתי לבודד שזה כרום שמשום מה לא מצליח להתחבר לסאונד. אם פתחתי VLC וניגנתי סרט, הוא השמיע את הסאונד.
תצא ותיכנס לחום.
נסגור את הכרום.
לא, מישהו רעיה למערכות.
זה V, זה חוק לא מצוין.
כנס ליוטיוב, בוא נראה שיש סאונד.
我专门留人票，2点哦是早上，早上5点，早上5点
，7000，很便宜了。
很便宜了7000多啊！
为什么我之前搜的都是4、5千？
你那不带行李票，我这个带行李票2个行李票呢。
很多人跟说
除非
这个，他是下午
最贵现在
0点7号，这还是有的。他最后之前跟那个我跟学生说。
בוא נחלף?
ואז בצד השני זה בדיוק.
אז כאילו הפעלתי VLC או הפעיל סאונד. לא, זה ספציפית אנחנו מפעילים גיבוי. זה אמור להיות השני.
אמור להיות מה?
עכשיו מה שאני שומע זה מהפודיום עצמו.
אתה בטוח?
כן. אתה שומע את זה מהפודיום.
אתה צודק.
זה גם די דומה הרבה דברים דומים למה שעשינו בתרבות.
זהו?
中管一反半开呀吧，公馆好像开的。
אתה צריך קרוס, תסתכל, זה
של מי?
יש לו רכיב Y ורכיב X.
可以把前面借回去。
是分2批，可以分2批的。那去6号的话，我就只能去2批的。
你专门把前面
你
借
要回来，但是他房年要1年，这最后1年。
房年定了，难道一定
要不住房年，都要扣2天学。4000人民币对于公积金现在是太难了。
你是公积金加4个，打成机票回来，打成7000的机票回来，把2个10个。
לא, אני מדבר. יש שביל. אבל המחשב עצמו כן הצליח להתקשר עם רמקול ספציפית לגרום שעשה
יציא אמרת?
כאילו ניגנתי משהו מהדסקטופ יש אחד מהסרטים פתחתי זה, לצורך עולה כמה שירים קדימה אתה לא משמע
זה לא פשוט רוצים לספר אבל כשאני מנחש דבר כזה אני כבר לא קובע באופן
ספציפית לכרום
נגיד אני זוכר שכשכתובות תנאי שפה קיבלה גם פתרון כל הפתרונות שלה אני
איבדתי אותך קצת.
אוקיי, סבבה, אני אסביר אני זוכר שכשאנחנו פתרנו נגיד מה דחים וכל זה אנחנו יצרנו את תנאי קבענו תנאי שפה כי גם פה כאילו אתה קובע תנאי
התקשרו נתחיל כדורגל, אני יכול ללכת.
בינתיים מנסים לבדוק למה אנחנו לא שומעים סאונד מהמחשב. ננסה לשאול שאלה מהבית, לא נשמע אותה. כרגע יש לנו תלמידה אחת שם.
אף אחד אף פעם לא שאל שאלה מהבית.
זה כבר שאלה.
למה לעשות את הדבר הזה?
然后踢到之前，
לא יודע, אני דיברתי לסדר. לא.
יש לך חוק עם
הקלטה יש?
יהיה.
ה-A הזה זה כל
יהיה או יש?
רגע, עושים ריסטארט
אני חושב
למחשב.
שיש.
כאילו מה אני רוצה
לדעתי יש.
בוא נתחיל.
לדעתי יש הקלטה. מה שאני עושה זה לא קשור לעשות.
אז אפשר לעשות
דוד,
הפסקה.
זה לא כל ה-A, זה דיורגנס של
דיורגנס
אריאל, גם היוטיוב
7
לא
号
עובד?
没有，有8号，有6个。
כי היוטיוב לא עובד כבר שבוע.
היוטיוב לא עובד.
לא עובד?
לא עובד. בינתיים. בימים הקרובים לפחות. בשבוע הקרוב.
וואי וואי.
海南主要是农学飞的过程。 3号有，5号好像没有，5号没有，4号也没有，3号有吗？对，4号没有，3号有，3号2号没有，2号没有，3号没学会了吗？啊，3号有，3号有，3号和6号都是海南的，对，一样价。
我妈是说的的，他说我妈是
就要不3号要不6号。我不要专业看波尔了，把它拿给多少来扣？是专业。 3点40亮2还没考完。
如果真的打算放一块，其实我也
你要是都放了有一个，我们要是在8月中旬啊，隔太远了。要是在8月中吗？隔的时间不短的话，我们肯定太长了。
找得到，只不过他在中间
3号人没有
很难找，哎，找到好像
想走回去，我主要是不想再买成普通道，
可以。
到天上玩票了，来回贵。
来回贵啥？也就200-300。So, after some technical difficulties, let's return to the point we stopped in the previous lecture. Basically, what did we do in the previous lecture? We tried to give a model that will describe the conductivity or the resistivity of a system of electrons in a metal. Now, Drude, as I said in 1907, came up with a very simple model. Basically, you treat the electrons as free particles, the same as particles of gas. You assume that you have an electric field that accelerates them. That's handled by Newton equations. And if we would have only that, why is that not enough? If I treat the electrons in the metal just as particles that obey Newton equations, put an electric field and see how they accelerate. Let's assume that they don't have interactions. Now, you're in the direction, but simply they'll gain infinite energy. That's not what happens in a resistor. The energy is conveyed as heat outside. So you add an additional term which tells you that every tau seconds they go through a collision and come out with an average momentum which is 0, meaning the energy is transferred outside as heat. And that's it. By these two simple assumptions, we got to the point where basically we can describe the connection between the density of current and the applied electric field. by NE squared tau, let's call it NE, divided by N. And that's known as the conductivity. Great. In this we have 4 different terms. The electron charge, which we are supposed to know. The mass, which we are supposed to know. The electron density, which we have no clue. And tau, the time between the collisions, which again we know nothing about. So if I'll perform this simple measurement, the connection between the applied electric field, or in another, just the applied voltage on the system, and the current, I won't be able to decide if the results that I obtain comes from here, they're multiplied. No way to know individually what is the contribution of each one of them. So we said, okay, let's try a different experiment or additional experiment where we apply on the system not only an electric field but also a magnetic field. And this is known as the Hall conductance or the Hall effect sometimes it's called. And all you need for that is take a strip, it's a finite quasi one-dimensional strip. You put in here a magnetic field, perpendicular in or out of the system. You apply an electric field in this direction, and then you have the electrons feel the electric field and the magnetic field, Lorentz force. And because the Lorentz force sends the electrons to the edges of the system, I'll get charge accumulation on the edges and an additional electric field in the y direction. Now I take all this input and put it into the equations of the momentum, which take into account both the force, the Newton contribution, and the fact that these electrons lose energy by heating, the contribution of tau. And we ended up with writing 2 equations. So we started from force heating, and since we are dealing here with a steady state, we end up with 2 equations. Steady state, the momentum doesn't change with time, so the derivative is 0. omega c is a constant. Those of you who remember something about the motion of a particle in a magnetic field know that this is the cyclotron frequency. And why is it a cyclotron? Someone knows here?
You put a particle in the magnetic field and move it to the other and the other, and that's how you.
Basically, a particle in a magnetic field, if you have just a pure magnetic field, will just rotate around at a given circle, size of circle, with a frequency given here. Okay, so we're left with solving it.
The frequency is constant?
Yeah, because everything here are constants. And if you want to understand why, you don't gain energy from a magnetic field. All it does is bend your velocity. It doesn't change your momentum.
And it doesn't change my velocity.
If it doesn't change your momentum, it only changes the direction of your momentum, not the size of your momentum. Okay, so all that is left is to solve these equations.
עצם זה שזה מסתובב זה בהכרח ציפלטרון?
No, I'm identifying. This is a constant. This just comes out from manipulating the equations. I just bring to your attention that the same combination of constants appears in the cyclotron frequency, and therefore I call it the cyclotron frequency.
So the time period is also constant.
If I take a particle with a given velocity and release it in a magnetic field, yes, or in a perpendicular magnetic field. If it's not perpendicular, it does a helix. Okay, but okay, so let's see, we have here dependence on E, the electric field, and things that depend on the momentum, and the magnetic field is hidden here. Okay, let's move the electric field to one side of the equation. And minus okay, let me multiply both sides by I'm allowed to do it. What do I gain by it? I get here before Ex sigma. Okay. Some of you probably are staring this. From where does this come? Just comes from the definitions. Basically, we should have written here P, choose which P, N E tau times N minus, right? We multiplied by N E tau over M. But what is P? And V. Okay. And what is this guy? J. So that's why we get what's written. Okay. How do we move from here? Now we go back and look at our system. What is JY here? This system at steady state.
It's steady state, no particles move, so 0.
Well, let's be a bit more exact. No particles move in the y direction.
Yeah.
So JY
Is 0.
it has to be 0. Okay, so let's make it even simpler. Okay, this we knew already. Okay.
Isn't it supposed to be a minus before the sigma e?
Mm, Yes, there should be a minus.
Sigma EX, and it should be minus that.
Yeah. We are now trying to.
In the left.
It should be minus, right?
Minus plus. So, but if I do this, I just okay, so this connection exists. Now, the experimentalist defined a parameter which is the Hall coefficient. That to confuse us, they call it also R. It's not resistance. Nevertheless, they call it RH. The H indicates the whole distance, which is
Why is sigma there? Shouldn't it be sigma over tau? It's sigma EX, shouldn't it be sigma over tau EX?
if I multiply by this, it's just E squared times this is sigma. Where do I have it? Here. Missing the minus there. So I'm taking what is written here. Jx drops out. And basically I'm measuring here only the density. It has no dependence on tau. And this is very nice because that's exactly what disturbed us. In measuring just the conductance, there we had a multiplication of n and tau, so we can go and do this experiment. Come up with n because E and the speed of light are known, hopefully. And it's a direct measurement of density. And how do I know this thing? Very simple. I measure EY. How do I know EY? That is just a whole voltage, the voltage that we measure from here to here, times the width. No, I emphasize that it's not resistivity. I started by saying it, that they called it R2 in order to confuse us. It's not resistivity, it's a coefficient. Okay, so great. So now I can close up everything, end up with measuring the density, electronic density through the whole coefficient, go back and measure the conductance or the conductivity, and I have tau. So I know everything about the system. So far, so good, except for one problem and one disaster. Because the problem is that the density of electrons doesn't correspond to Z times E. It's not as if every atom in the system, in the metal, contributes an integer number of electrons. Which, if you go back to our initial assumptions, we said some of the electrons are in the core don't participate, and those that are in the outside shell participate, and then we would expect to have an integer number of electrons per number of atoms in your system, and it doesn't correspond. It goes somewhere between half and 3. Someone who's very interested in can check it in Ashcroft in the first chapter. There's tables. Okay, why do I say it's a problem but not a catastrophe? Well, we're not so sure how the electrons are connected in the covalent bonds. Perhaps they are part of the time there and part of the time not there. It's a question, but not a great, not something that throws all of our assumptions out of the way. Something that is much worse is that copper and aluminium, which are two respected metals, have an opposite sign of the whole coefficient. So what does it mean? That if we assume that one of them, I think copper, the charge carriers are particles with negative charge, in aluminium it's with positive charge. That's a catastrophe. Because how can you explain it? Everything you started from electrons. Electrons are, well, if we know something about electrons, is that they have a constant charge. How could we come out with a charge carrying entity here which has a positive charge?
Both. The whole, you think about the holes moving and there's particles.
Yes, but in Drude's explanation, there's no holes, nothing of that nature. So it tells us that we don't understand something about what's happening in this system. Okay. Nevertheless, that gave us some probe into looking what's the density and some understanding on what determines the conductance, which is tau, the time of scattering. Okay, before moving on to better theories and do the theory, I want to look on another question which we want to understand about metals. Okay, except for this property that metals are good conductors, or at least decent conductors, they have also an additional property that we are all aware of, but perhaps not all the time thinking about it.
Heat conductance?
Heat conductance, yes, but I'll get to it further on.
The ability to bend them?
Yes, but that's not necessarily an electronic property. It has also to do with the lattice. Very simple.
Melt?
Electric fields don't propagate in them. That's why your windows are not made out of metals. And that property you can pull out from the Drude's theory. And not only that, if we try to propagate very high energy electric fields or electromagnetic fields, there is a frequency where the metals become transparent. And the Drude equation gives us, or the Drude theory gives us some way to quantify what is that frequency. Okay, so let's see how we do that. And if you don't believe me, think a minute about the fact that to stop wavelengths in the visible light, a few hundreds of millimeters of metal is enough. But if you want to block X-rays, you have to have a serious width of the system. When they had here an active X-ray in the floor above, at the end of the run they had to put a piece of 40 centimeters of lead to stop it. So we need a thick metal to stop this radiation. Okay, don't worry, I think it's not working for the last 20 years. So. Okay, so AC conductivity. So if you remember anything out of your electromagnetic course, you'll expect me to write down electromagnetic waves that has an electric component and a magnetic component which depends on time and on position. But I'm interested here in the case where I have a long wavelength. Long wavelengths beyond visible light. What is the wavelengths of visible light?
500 nano.
500 nanometers or 5,000 ags. Between 700 and 400, somewhere around there. So, if I'm thinking about a typical piece of metal, that's something of few hundred atoms. If I'm looking on radio waves, could be hundreds of meters. So I'm forgetting about all the complications of electromagnetic fields that you have studied in that course, and I'm writing down an extremely simple equation for the electric field, which is just an amplitude times the frequency. And then, okay, so I forgot about, this should depend on R, we know, the position. We assume that the part of the system that we are considering here is much smaller than the wavelengths, and therefore I'm taking the amplitude just as a constant. What happens with the magnetic field?
Same thing, it's just perpendicular.
Even worse, I'm forgetting about it completely. Why? Because magnetic fields are much, much weaker, have much less influence on the motion of a particle than the electric field in AC. Because the connection with the permittivity constant makes it much smaller.
There is one over the speed of light somewhere, I think.
Something like that, yes. So I'm left with this simple expression, which will make my life much easier in solving the behavior of the electrons. Okay. I'm writing back my old assumptions of the Drude theory. I have here no magnetic field, so that's all I write. Okay, I'm looking on this differential equation. Here, of course, I can't anymore assume that there is no change in the momentum. I'm putting an AC field which changes with time, so the momentum will also change with time. But what can I assume about the behavior of P?
So,
No, it's not conserved. First of all, because of this. It can't be conserved. Can assume that it is in phase with the electric field for the simple reason that we threw out the dependence on R, so there's no reason here that it will lag behind. So we're taking a solution where you have something, an amplitude which depends on omega. And let's see what we get here. Put here a minus just for simplicity. Okay. And if I will multiply it in order to get J, and we remember J is just written here. So I'll multiply it by constants, I'll get here J omega. So what did I get here after these algebraic manipulations?
Is it supposed to be a plus?
In the denominator with the p omega.
First of all, they're supposed to be here. Okay, let me. I have suspicions that I've missed a minus somewhere. Not very essential. You can go and check it up in Ashcroft or do it by yourself and clear up the minus. But what is important here? What is sigma 0?
The conductivity, you measure it.
I'm at. That's exactly the conductivity that we used previously, but now I'm adding a 0 to emphasize the fact that it's the DC conductivity. Okay? That we developed with a steady magnetic field, not an oscillating one. So this is what's the first thing I have to check about this result?
Units.
Excuse me?
Units.
Even simpler. Units I know that works here. Why do I know that units work?
Conductivity times selection.
Because this is the units of conductivity and this doesn't have units because omega and time have no units and one certainly has no units. So units are okay. From the point of view of simple physics, what should happen here? If the frequency goes to 0,
Then a constant electric
I have to go back to the DC result. Does it? Yes, certainly. Omega goes to 0. This falls off, and we have the DC result. So that's fine. Okay. But what does this thing mean?
Phase?
It means phase. And now we have to go back to Maxwell's equation in order to understand what this phase means. So we started with a very simple assumption, got a rather simple result, but let's try to understand what this result tells us. So, a refresher on Maxwell equations. It shouldn't be news to you.
הרשום שם זה קצת שמאל, דיווגנס של E שווה לרוב ולפלמה.
Epsilon.
לא אפסילון אפס.
בחומר.
If you're in a material, we'll use it. Okay, I'm taking this equation and performing an additional curl. You have seen it in the development of an electromagnetic wave. So what did I do here? I just took this equation, applied an additional curl, used vector differential identity is then moved to here. If you want to convince yourself, refresh what you did in last year, I guess. And here I just applied the curl on B. Okay, now I'm pulling out curl B from here in order to eliminate the magnetic field out of the game. Okay. Just inserting this part of the Maxwell equation into here. Did I miss?
That's only the divergence. Way into zero. Yeah, missing zero.
Here I have no, this is the usual way that you develop an electromagnetic wave that you have done in electromagnetism. Let's just substitute E with our assumption that E is equal E omega I omega t minus. So what did I do here? Inserted the definition of E here and here, and took the connection between J and E omega from here. That's all. Okay, so we have a differential equation on the electric field in our metal. Well, I have here two limits. One,
Minus. And there minus sign missing.
pulled out
Oh no, wait.
where? Here?
No way. Sorry.
No, because of the derivative. You have I squared pulled there. Always the second derivative doesn't change the sign. Only first derivative may change the sign. Okay. Okay, I have here basically two limits. Let's start actually with the limit of high frequency. So I sigma omega divided by epsilon omega, the term appearing here. Just inserted the definition of sigma omega. And since this is much larger than 1, I can forget about 1 and write it down as and what does that tell us? Omega is much larger than omega p. So we have here a real term. We ended up here with something with a real term. And what does this type of differential equation with a real term end up as?
Waves.
Propagating wave. On the other hand, for then I'm left with an imaginary part. And what does an imaginary part? Exactly. An attenuated wave just doesn't propagate. So for metals, the usual situation, unless your frequency is very high, your wave doesn't propagate into the metal, and that's another result from Drude's physics. Actually, it's not surprising. Basically, if you are trying to propagate an electric wave through a sea of electrons, what will happen? The electrons acquire the energy of the wave, and nothing propagates. The interesting part is that if your frequency is so high that it doesn't have time to respond to the waves, then it goes through. So that's another consequence of the Drude theory. Metals are not transparent unless the frequency is very high, and then you can go through it. Okay. So we have seen that Drude's theory has a serious problem, especially positive charge carriers from the Hall effect. How can we explain it? Well, with your experience with the beginning of the 20th century physics, how do you explain something that the classical theory doesn't explain?
Quantize something?
You move to a quantized theory. And we'll do it actually in two stages here. First, we'll do the simplest thing that we can think about, which is simply to quantize Drude's assumption, meaning instead of classical particles in a box, we will have quantum particles in a box. It will turn out that that's not enough, and we have to take the lattice potential into account. But to some of the problems that we have, the free electrons in a box will give us an answer. Okay, so let's start with the first steps that we have there. Schrödinger equation. Where is my box?
Metal cube.
I haven't yet inserted the boundary conditions. So I'll have to, in order to get my particles into a box, I'll have to define boundary conditions. So what are the boundary conditions? Instead of putting hard wall, why don't I put hard walls? because I'm not interested in surface effects at the moment. And second, I would like to think about problems of transport. And I can't transport electrons if they are in a closed box. They don't go anywhere. I'll apply an electric field, they'll get accumulated at the two edges, and that's that. That's not the situation where I connect them to a battery or whatever. Okay, so what will be my boundary conditions? Periodic boundary conditions. All of them stopped writing. And the same if I play with Y, and the same if I play with Z. Okay, all it says that if I go a distance large L, I'm back at the beginning. What do I gain with it? As I said, one thing is about transport problems. The second, as old hands in quantum mechanics, why is this better than taking a finite or an infinite system?
So we can use a finite number of waves for a solution.
Exactly, and I don't have to worry about Dirac conditions of orthogonality and so forth. Can use plain old, well-behaved Chronicles conditions. In the end, I can always take L to infinity, but in the intermediate steps, it's always easier to take a finite periodic systems and take L at the end to infinity. Actually, the same thing is done for quantum field theories and so on.
We need to renormalize.
Excuse me?
Well, that was all renormalization in quantum field theory.
Yes, but here you don't have problems with renormalization for. Well, I don't want to go into the conditions, but anyway, when I'm doing the math for quantum field theory, it's always easier to start from a periodic system and eventually go to an infinite system. Okay. Won't come as a revelation to use that as a plane wave solution. The fact that I have periodic boundary conditions, as we have seen for our phonons, requires that I'll have here quantization of K. with an x and y so on and so forth. Why these numbers? Because I want L in order to fulfill the periodic boundary conditions. We have seen it already in the reciprocal lattice. We've seen it for phonons. Say any wave in a periodic boundary condition gives you a quantization of this form. The question still here?
איך אין פה ל-K הזה בסוף?
Excuse me?
ה-K הזה בעצם מתנאי השפה.
Right, I should have written just ky, kz, sorry, kx, ky, kz. But because I want periodic boundary conditions, it's not any value of kx or ky or kz, it's this quantized. And then if Lx, Ly, and Lz go to infinity, it's back to a continuum here.
בעצם אחד הפתרונות הפורסים, נכון? כאילו אתה עושה עכשיו בעצם פריסה עם כל הפתרונות באורתוגונליות, או שזה כאילו מבחינתך הפתרון?
For any nx and y and z, it's psi here is an eigenvector that fulfills the equation. What is the energy of this wave function?
K squared.
Remember, it's a vector. So if I'm looking on the possible solutions or the possible states of the system, and the distance between each point here. For simplicity, I'm assuming that Lx is equal to y equal to z. Otherwise, it's not a rectangular, it's other square. Sorry, it's not a square, it's a rectangle. Okay, what happened with kz? It's perpendicular, and to avoid confusion, I won't try to draw it. Okay, now, what do we know about electrons? Electrons are fermions. Right? So at zero temperature, which states will they occupy?
רק עד אנרגיה ספרדית.
Well, they'll occupy the lowest energy states, but not all of them could be at state zero, just because they're fermions. At the moment, I didn't even mention that electrons have spin. Without spin, there will be one electron on each such point. If I have spin, so I'll be able to pack 2 electrons on each point, but not more. That is a basic property that fermions have. So, what is the minimal energy here?
0.
No, if I have more than 2 electrons, it can't be 0.
How many atoms do you have?
Well, correct. It depends on the number of electrons that I have. If you give me the number of electrons, what will I do?
We'll fill up the energy levels for
I'll start populating these
lower energy.
states, and I'll try to fill up the lowest energy states that are open. So the first I'll fill up this guy, then these 4 guys, and so on and so forth. If I'm looking on a large scale, I'll have basically I'll fill up all states within a certain radius. Which is supposed to be a circle with the same radius from the center. And I'll call this radius K for me. I'm filling up each K that is smaller than K for me. On what K for me depends? K for me depends on the number of electrons that I'm trying to populate these states by. So let's start with a couple of definitions. So if I'm looking at some volume omega of the K space, the density of states is simply omega over 2 pi L to the third. Sorry, that's not the density, that's the number of states. And the density of states what do I do in order to get the density of states?
Divide by the area.
Divide by the volume or area, whatever you call it. Depends on dimensionality. Divide by omega. So it's just L to the third divided by 2 pi, which is V over 8 pi. So, this is the volume of a sphere with radius k Fermi, right? What is this? The volume times the density of states. Number of states. What is the number of states? The number of electrons that I have. And here we'll remind ourselves that each state can occupy 2 electrons because of spin. And now stick in the definition of the volume and we'll get a connection between K Fermi and the number of electrons. So we have 2 times 4 pi. And so, tell me the density of electrons, I'll be able to tell you K Fermi. Okay, you can stop me and ask a very simple question. Who cares? What is the most essential new elements that quantum mechanics has inserted here to my game. Well, and we'll emphasize it in the next lecture, but I want to give you a taste why are we doing all this calculation. I take a classical electron, apply a field on it. No problem, I can calculate what is its new momentum, what its new velocity, everything's fine, as we did in the Buddha. Here, if I'm going to this electron and telling him, well, I'll add you some quanta of momentum. What does he answer me?
Now I know what's my position.
Sorry, I'm not interested because it will move me to here or here or here, and all these states are already occupied. Can't do anything with it. Not useful to me. The only electrons that are ready to play games with me, meaning agree to accept an additional momentum or additional energy, are those on the fringe at the Fermi, at K Fermi, because above them they have open states. They can absorb or give back energy or momentum or anything. We'll see, quantify it in the next lecture, but here you have already the beginning of the answer of our first non-catastrophic question. Why the number of electrons that are playing the game of conductance is not an integer multiply of the electrons in the outer shells of the atoms? Because that's not relevant for quantum mechanics. I should ask the question, how many electrons do I have that are ready to participate in conductance? And that's not the total number of electrons, it's the number of electrons that are close enough to K Fermi in order to take part in the game. So when we're measuring density, it shouldn't be an integer number. It should be something that depends on K Fermi. So we'll elaborate on it in the next lecture, but we can start to see the first contribution of quantum mechanics to understanding conductance of electrons in this system. Okay, we'll stop here.
מה אתה דבר שם? פאי בריבוע n?
Yep. So the n divided by v, and we'll get 3.
שתיים ועשרה או שתיים?
שבוע שעבר כבר שתיים.
אני בוא נגיד 2:15.
המעגל הזה זה
No, it's LQ.
לא תתכן שני פאי פקל?
No, V is L to the third.
אוקיי.
איך אתכם סיפור מצבים? אומגה כאן זה המספר מצבים,
לא, אומגה זה הנפח.
אומגה זה הנפח של הכדור הזה,
כן.
זה השני פאי KL בשלישית,
זה מספר נקודות
נקודות, מספר מצבים שונים, זה הנפח כמספר מצבים.
אז כל מה שאתה שואל כמה קוביות קטנות כאלה אתה דוחף.
כן, לא יודע, במכניקה סטטיסטית כל הזמן.
כל זה עשיתם במכניקה.
כן, כן, זה כל מאוד מוכר לי, אז כמה, לא יודע כמה, הבנתי את זה לעומק.
אין מה לעשות, כשלומדים קונספטים חדשים, בסיבוב הראשון אתה תופס איזו תמונה מאוד גסה, אתה רואה עוד דוגמה, זה מתחיל להסתדר לך. מה לעשות, המוח האנושי ככה בדיוק.
לגבי הפתרון, כמו שאמרת עם ה-phi r, או מה שהיה שם למעלה, אני זוכר פשוט שכשאנחנו נגיד דיברנו בכל הקורסים של מחלקה סטטיסטית, ממפיס שלוש כזה וניחשנו פתרונות, קיבלנו צורה כזו של פתרונות כמו שאתה רואה פה, ואז מה שהיינו עושים היינו נגיד אורתוגונליות, שהיינו עושים נגיד הטלה כדי לזה. למה פה נגיד אנחנו לא עושים סוג של הטלה מסוים?
תיקח K אחר ותבדוק שזה אורתוגונלי.
כן, אבל כאילו מה אתם מנסים למצוא כאן?